Stan Gibilisco here to talk about radio frequency speech clipping as a method of improving the intelligibility of a single sideband voice signal, particularly applicable to amateur radio communications, but also to some extent in other services that take advantage of single sideband. This is similar to audio speech compression, except it's done in the radio frequency or intermediate frequency stages of a single sideband transmitter. You start with your ordinary uncompressed voice single sideband signal. Actually, that's an important thing to note. Voice, not music, not digital data of any kind being fed into a single sideband transmitter, but just old ordinary speech, just like what I'm doing on this video. Comes in and you amplify the signal. It's one of the amplification stages. It's one of the intermediate frequency amplifier stages, conventional amplifier, that business. Then the critical part of this system is the clipper. Now what that actually does is it clips the peaks of the signal on your transmitted single sideband. It literally chops them off. So if your single sideband signal as a function of time looks like this, suppose this is your power graph as a function of time. Time on the horizontal axis, power on the vertical axis. That's your voice signal before it's clipped. You amplify that signal to make it literally too loud so that the peaks are too high, and then the clipper circuit just chops them off. Now you're going to get what they call flat topping if you do this, and that flat topping is going to greatly increase the bandwidth of your single sideband signal. Normally the bandwidth of a signal like this is about 2.7 kilohertz. The audio components of the signal range from about 300 hertz to 3000 hertz. That's the only range that you really need to effectively convey a human voice, so they have more or less agreed upon that standard. So it's a 2.7 kilohertz wide signal as it would appear on a spectrum analyzer when you look at it in your laboratory, which I'm sure you have, right? In any case, once you've clipped that signal, that bandwidth greatly increases. It might be in excess of 100 kilohertz wide. You'll hear the ordinary voice, and then either side of that voice, those flat top transitions, those abrupt corners on the clipped wave will produce this crackling sound. And if you may have heard that kind of splatter. That's what that's in fact called, and that's a pretty good name for it. It pretty well describes what it sounds like. Sounds almost like rain falling on a pavement or something like that, splattering. And it is a mess, and it's also illegal. The Federal Communications Commission here in the United States frowns upon a signal that has that characteristic. So in order to prevent that flat topping, you need to use a brute force filter in order to limit this bandwidth back to the 2.7 kilohertz that it's supposed to be. So you're almost, in a case like this, trying to increase water pressure through a pipe of constant diameter. You do get more pressure and you get a higher water speed, but your pipe is only so big around, and that filter ensures that you're not going to get water splattering out of that pipe and going all over creation. You need to have that filter. This method isn't used very much anymore to the best of my knowledge, but it can still work if it's properly engineered. It can improve the intelligibility of a voice if you don't overdo it. If you overdo it, you'll get the same problems that you would with analog audio speech compression. The background noises and your breathing and all of your little mouth movements and everything will become amplified to the extent that they actually interfere with what you're trying to say, and it defeats the whole purpose. Another thing that this process will do, as analog audio speech processing will do, is because it increases the average power, it will increase the work, the amount of work that the subsequent stages afterwards here have to do. So you have to be careful that you don't exceed the ratings of your driver and your final amplifier stages and cause them to overheat and malfunction, possibly even burn them out. You have to be careful when you do something like this that you don't overwork your radio frequency amplifier circuits, your power amplifier circuits. But it can be an effective way to get more bang for your buck in a single sideband signal, particularly for amateur radio operators who are limited in the amount of power that they can use. I believe it's 1500 watts peak envelope power. Well, you can boost the average power without going over that 1500 watts and literally get more bang for your buck, as it were. I think I've worn that phrase out, eh? Stan Gibilisco signing off for now. Until next time, so long.